Yeah, good morning everyone. Firstly, thanks for having me along to speak today. I'm from DST in the Missile and Space Propulsion Group, and I'm here today to talk about high-speed systems and the responsive space access. Also give you a context around the technologies that DST are researching currently that are enabling these next generation missions. So I'll give a couple of examples of high-speed systems. So in 2004, NASA, as part of their HyperX program, conducted 2 flight experiments of their X-43, which you can see on the left, which is a scramjet front end powered by a Pegasus booster, which was launched off of a B-52 aircraft. It successfully achieved high-speed flight for over 12 seconds, attaining a speed of Mach 9.6 at 33 kilometers. And then subsequently, in 2010 and 2013, they again, with Boeing, performed testing of an X-51 Wave Rider scramjet engine. A Wave Rider generates compression lifts off the forward inlets, and this successfully achieved high-speed flight for over 3 minutes with a speed of Mach 5. In both of these scenarios, though, it required the use of a booster that, in total with the system, was almost 2/3 of the stack mass. Having such a large booster requirement greatly restrains what you can have for your front end, which is where all the range and speed comes from. Also constrains that volume environment, which is why it had to be launched off of such a large platform as a B-52. In terms of commercial space access, the civilian sector relies on space-based assets for on-demand communication, location services, and data exchange. And this is a similar story in the ADF, where satellite provides communications, position, navigation and timing, intelligence, surveillance, and meteorology, which are all critical for battle management systems, as well as air and missile defense. The ability to insert new and replace existing space-based assets in a cost-effective, timely and geographically agile manner stands to afford significant strategic advantage for commercial and the ADF as well. This is really the basis behind responsive space access. So traditional space access is very long lead times in excess of 12 months, heavy payloads, tons, very high costs, and also requires significant ground launch infrastructure. However, there's a new paradigm of swarms of microsatellites operating in unison, which could be serviced by responsive space access, which is characterized by lead times that are in the order of months, greatly reduced costs, payloads in the order of hundreds or even tens of kilograms, and also highly tailored orbits, so using mobile or air launch platforms. For DST, whether it's developing high-speed systems or developing capabilities to support responsive space access, faster and advanced propulsion technologies enable us act as a critical enabler in the pursuit of delivering payloads further, faster or higher, and with increased operational flexibility. Responsive space is focused on providing highly tailored orbits using mobile launch facilities or air launching, such as which Virgin Orbit, seen in the top of the rightmost image, are planning. So Onscreen is a very high-level taxonomy of chemical propulsion classes and subclasses. I'll talk today around mainly missile, but I've also got on screen gun propulsion systems and how these apply for high-speed systems and responsive space access. So DST has a broad range of experience across many of these classes of propulsion systems, but mainly in the development of solid propellant rocket motors. And recently we've started an engagement with in-country academia and industry around pressure gain combustion, or you might have heard of rotating detonation engines, with international partners as well, other government agencies too, which I'll talk to about later. One of the STCs, the Science and Technology Capabilities at DST, Disruptive Hypersonic Technologies, maintains world-leading research and testing capabilities in scramjet engines. Onscreen is a very broad range of the classes, and not all of the classes or even subclasses are included here, and each propulsion class has a pro and con depending on what your mission requirements are. And these are not limited to what the range, the velocity required. Do you need thrust modulation? What's the mass of the payload, both of payload and also the total mass of your system? What maneuverability requirements you have? Volume and geometric constraints are also really important. Safety and storage, and also depending on the application, how easier and what is the cost of manufacture. Even being aware of the mission requirements and given the broad range of technology options, trade-off selection of the most appropriate class of propulsion system is never always trivial. So on screen, I've got an overview of the 4 main classes of propulsion systems and the 2 applications. Now, apologies, it is a bit of an eye chart here, but the selection of your propulsion system is dependent on application, but also things such as costs, responsiveness that you want, robustness, and so forth. So each class has pros and cons when compared to against applications in high-speed systems and responsive space access. So for solid rocket motors, they are the leader in storage. They're highly tailorable. They can be used for air-to-air, air-to-ground missions, and they're also a necessity for high-speed flight still. However, they don't have thrust modulation, at least easily, and they generally have less performance versus liquid systems, which is why they're not in use heavily in traditional or responsive space access. Liquids have excellent performance. They have great throttle ability for low cruise or ascending through high drag regions. They have great volumetric efficiency, and they can also be used in multi-role applications. However, they're very complex. They have significant refueling challenges as well, and potentially dangerous storage of at temperature chemicals as well. So they're traditionally not used for mission systems or military applications, but they're still the workhorse of traditional and responsive space access. A downside is they still require significant ground-based infrastructure, but with the innovations I talked about with mobile launch, it's starting to alleviate this. A hybrid rocket motor is the best of solids and liquids in that it uses a solid fuel grain with a liquid oxidizer, meaning that it still has excellent storage, but it now can be throttled. A downside of this is it has a generally low fuel burn rate. So in order to augment the thrust, you need to create a geometry that has a very high surface area, which reduces your fuel loading amount. At the moment, it's finding a niche in responsive space access. Because of the smaller payloads required to orbit, the thrust requirements are much less, so we're starting to see it used a little bit more. It's also beneficial for manufacturing because the fuel grain itself is either a wax or a rubber, and this can be 3D printed with today's technologies. Gilmore Space Technologies are an example of a company who's doing great work in hybrids in Australia. Finally, air-breathing systems have the best overall performance, and this is mainly due to they don't require an oxidizer. They can ingest it from the environment. And they also have the forebody is a compression stage, so they're great for long-range cruise applications, but they're not quite relevant for responsive space access. People are talking about using them for the holy grail of space access, which is a single stage to orbit, but there's a lot of technological challenges before that actually occurs. There's a range of science and technology areas available for exploitation. So if we support this by using optimization techniques along with materials development, both of the energetic materials and the inert components, as well as manufacturing techniques that allow us to exploit the benefits of the same, we're able to improve the energy density, have lower mass systems, and see step changes in performance and operational flexibility. This is occurring at the moment at DST, both for high-speed systems and responsive space access. So we can choose one of these classes of technology areas to try and invest in research and development, but that also comes with small performance increases because they're very well-defined areas. If we run optimization or machine learning across multiple of these areas, we stand to gain better exploitation and benefit from the same. So for example, SpaceX, which is a commercial space company, are doing great things in their liquid rocket systems, but their great benefits come from the fact that they've developed this as well as computational modelling of their trajectory, coupled with gyroscopes development, which means they can land a motor that's just put something into orbit on a barge at sea that had been travelling Mach 20 or so. So Onscreen is a simplified development cycle for a solid propellant rocket motor. It's typically a very time-consuming, arduous process that requires numerous iterations. And there's also a set of competing requirements. These are mission requirements, system performance, even sub-component requirements. Often they're separate teams who perhaps don't integrate too well and are not willing to share the mass budget. As a result, the overall system itself suffers. Often through life support of the system too for military applications is seen as a bit of an afterthought. So at DST, we created a trade space study and motor design tool known as Seaghost, which performs an iterative development over all of these things on screen, including the propellant itself, the inert components, then it integrates and optimizes for a design. Coupled with spot checks for materials, this gives us the ability to look at a solid rocket design very quickly. Typically, propulsion systems are bound by the derived system requirements. However, if we run an engineering process, a systems engineering process over the top, we can achieve high performance system gains. The Seaghost tool sizes a propulsion system as a solution to requirement, be that requirement this amount of payload to orbit, or this speed for a high-speed takeover Mach number, or even a warhead that needs to be carried. So solid rocket motor design is inherently coupled, and its design and performance parameters operate in a non-linear fashion. So it's really difficult to know how this affects that. So typically it's done with an engineer or a scientist in the loop who understands that whole iterative cycle. So I'll give you a bit of an example. If we change the propellant grain shape of a rocket motor, maybe star or a center burning or end burning grain, then this changes our internal pressure time and thrust time curves that we get out of the motor, changing our overall kinematic performance. We have high thrust environments and high dynamic pressure environments. If the internal pressure of our case is really high, then that changes our burn rate, and it's an exponential change, which results in higher acceleration and changes our overall burn time of the motor. If we ramp up the pressure inside, well, now we need a stronger case to contain that pressure, which buys into the amount of propellant we can actually carry with us. And then we're carrying more dry mass as well. So this is less acceleration, less performance. We also need to take consideration of how that strain in the pressure works. And then in terms of the rocket motor case, if we have a large web, which is the distance between the bore and the outer surface, then this results in higher stress and strain and increased risk. Even the way we fly the system in terms of its aerodynamic properties changes the overall performance. So by applying optimization techniques over the top of the development process with underlying physics, this is known as NetNested Optimization and is present in our Seaghost tool. So the Seaghost tool allows us to design a rocket motor and fly it in combination with detailed engineering physics models underneath each, which allows the output of accurate models in regards to mission and design limitations. So inside the tool, there is a grain analysis via 3D grain regression rate, case analysis via netting of each layer of the case, material properties, and also a detailed combustion model, which includes an erosion model as well as overall combustion efficiencies. Included in this as well is an aerodynamic model for the flyouts, which includes a 3 degree of freedom flyout model and coefficients for aerodynamics, which are either derived experimentally or computationally. Overall, this gives us the ability to rapidly sweep the trade space and come up with very limited, highly optimized designs for further investigation via FEA and testing, which is typically very time consuming. So we can develop a design, but what this also allows us to do is look at prioritization of R&D. So we can ask ourselves the question, well, is it worth investigating a 5% increase in energy density for our propellant? How does this one subcomponent change affect the performance of our mission, as well as how that arrives at the system level? So we can gain better than the sum of the individual parameters, due to the highly coupled nature of designing both the motor and then the way it's flown as well. So we can exploit the improvements at a system benefit. So for example, if we improve case materials, we can operate higher pressures, which mean we get better thrust time curves, better acceleration at altitude, that we can have enhanced propellant densities inside the case as well, better propellant loading, and we can also have better burn time. So it's a really synergistic way of looking at solid rocket motor development. In addition to this, we need to have a look at advanced materials for use in the motor space, both for high speed and responsive space access. The way we do this is looking at the pros and cons of a range of advanced materials using traditional testing methodologies. We can also feed this back into our CGOS tool to give it a range of options to select. So in the images above, we tested insulation and case materials, assessing these materials for the maximum strength to weight ratio, obviously very important for space access, how it bonds to the propellant, how it tolerates extreme environments and how it responds to ablation and erosion rate, and how it can tolerate whole of system changes such as thermal expansion. We test this using torch tests, material testing, bond strength testing as well to ensure that there's sufficient stress relief and ensure that we have the required manufacturing tolerance, the strength, and also, most importantly, erosion resistance of the same. It's a similar process with nozzle development. So nozzles in rocket motors are typically made of graphite materials because it's cheap. However, over the course of the operation of the motor, you'll start with a fairly narrow throat, which due to the erosion rate will start to actually change in size, opening up, which drops the pressure inside the case. So there's a bit of a trade-off there. Typically, they also contain quite a bit of the overall mass of the system as well. So in-house at DST, we perform subscale testing of advanced materials. We included these in in-house flow modelling tools that we have to try and reduce the flow losses before moving on to computational fluid dynamics and finite element analysis of the same to produce optimised designs that are, most importantly, reduce mass and also reduce length for volume-constrained environments too. We can then provide these limitations back to the solver that I talked about before, and then we can manufacture them and test them in our, it's known as a BATES, it's our in-house rocket motor. This process led to the development of an Australian high temperature, low erosion material that is still currently being investigated. So propellant development is a complex mix of binder, fuel, oxidizer, plasticizers, ballistic modifiers, bonding agents, and catalysts. So there's a real balancing act between the requisite performance that you require out of your missile system, as well as other requirements such as the signature required, how stable you want the mixture to be, the ignitability of the mixture, what's the burn rate, what's the sensitiveness to external stimulus, and what is the useful life of that propellant. So the ideal propellant on paper might not be achievable in reality. Painstaking trials and adjustments are required to ensure that the propellant is consistent and can be used in the required grain form, star or center grain, as required. You also need to ensure that the propellant operates in unison with the case and other inert components as well, such as the nozzle and, very importantly, the ignition system too. The grain design, so the shape of your grain and any stress relieving features that you might have, and the propellant choice itself, you need to ensure that the pressure that's released as a result of burning the grain doesn't exceed that of the case or the joining components of the case as well, be it between the case and then the nozzle itself. Also important is to look at the efflux produced by the propellant and ensure that when it meets the nozzle, it's not in a form that can start to damage the nozzle, potentially eroding it any further and reducing your overall system performance. You also need to ensure that the system as a whole and the propellant that you've chosen can operate in the environments that it's likely to see. For example, an air launch environment, starting from the tarmac and going to altitude, can be a thermal change of over 100 degrees C coupled with severe vibration environment too. And this all has a damaging effect on the propellant, which changes over its entire life. You create further restraints if you look at a full S3, a safety and suitability of in-service items, and have to apply robustness testing on the propellant. So at DST, we've in recent times exerted considerable effort to develop propellant systems that maintain outstanding ballistic performance while also are robust enough to survive the extraordinary challenges of a tactical air launch environment. You also need to design the propellant and how it performs over each stage of that life cycle. We also test for how the overall system responds to external impacts such as fragment impact, slow cook-off, and sympathetic detonation, that sort of thing. So it's often a trade-off between how safe is the item for use in the field and how much performance that you wish to actually gain from your system. So I've talked a little bit about the material characterizations, and we're very interested in developing relationships between, on the left side of the screen there, the molecular level, the bulk properties, and the system performance as a whole. Identifying these relationships allows us to build up trade studies and identifies any potential life-limiting factors that we might see in the system that we've developed and how we can age the motors to assess these life-limiting factors. So I really wanted to show the relationship between the molecular level, the bulk properties, and the system performance. So typically if we have an item that might have been in service or it's a new propellant that we've developed, we'll perform bulk properties testing of the propellant and try and develop relationships between how things at the molecular and the bulk property relate to the system as a whole. We can test very cheaply at the bulk properties level. It's highly scalable and also allows us to have some prediction in the future, but testing at the system performance level means we either have to use an entire round or get one out of the fleet for test, which is expensive and requires the use of very high-level facilities as well. And this is the basis of through-life health assessment of in-service rounds. So a drawback for classes of classes of propulsion systems for both high-speed systems and responsive space access is the safe storage of the same. So solid rocket motors are the overwhelming choice for a number of reasons. So in the military, you want to ensure that when you're pulling an item off the shelf, if it has sat there for some time or potentially been exposed to environmental extremes, that it's going to work as required. DST has a bit of a history around in-service surveillance, and I personally worked on the NOLCA rocket motor development program and the ASRAM captive carriage extensive program as well. So in the slide here, we start off with propellant properties, mechanical and chemical in our test laboratory before moving to structural, thermal and dynamic modelling of the same. This allows us to build up a predictive capability of how a propellant is going to perform in the future. We couple this with accelerated aging of propellant samples and overall systems as well. However, when we do consume a sample, it is consume a round, like I said before, it is very expensive and we need to use high-level facilities. But in-service surveillance results in significant cost savings and provides assurance of the safety of the round to defence. So since 2012, DST has had an active collaboration with the US Air Force Research Laboratory, or AFRL, on all science and technology areas related to advanced tactical booster technologies, which we're able to leverage into application spaces where very high performance and system robustness is a prerequisite for success. The key S&T areas that have been accomplished by the program, they mirror what I've been talking about previously. This includes the high fidelity propulsion system design and optimization of the same to try and streamline this process, as well as propulsion materials offering increased thermal robustness, mechanical strength, reduced weight and volume requirements for overall system performance benefits. Finally, the development of a high performance propellant with large web thicknesses, high propellant mass fractions that are structurally robust when exposed to high vibration and tactical temperature cycling. So across each of these technologies, they've delivered a number of innovations to satisfy the requirements that I've referenced on the previous slide. One particular noteworthy piece is that as we've done this in collaboration with each of these technology components, we've been able to assess changes at the sub-component level to how this changes the overall system level. Materials side, the advances that we've made here have allowed for reduced weight, robustness, and the use of a higher propellant mass, so overall performance in our high-speed systems. But many of these systems, while they were applied for high-speed flight, have been applicable across domains that operate in the air, land, sea, and recently space access domains as well. So recent efforts in advanced materials and then manufacturing techniques necessary to fully exploit these benefits stand to introduce into service new classes of future weapon systems with better performance and operational flexibility than can be offered with today's level of technology maturation. So some of the key technologies here include nanoenergetics, structurally reactive materials, coupled with processing technologies that include resonant acoustic mixing, or RAM, and 3D printing, or additive manufacturing of energetics. A subset of these technologies are anticipated to significantly lower the cost of entry for the munitions manufacturing piece, which in Australia, this leads to a diversification of the supply of advanced munitions and also provides security of the war stock as a result. So starting with 3D printing of energetic materials, there's currently a global interest in this space across all classes of propellant, from gun and missile systems to explosives and also to pyrotechnics as well. And this growth stems from the magnitude of the performance gains that can be realised if we start to use previously unrealisable geometries, multi-component structures that are currently not feasible with today's processing techniques, allowing us to tailor the energy release out of our system. So for propulsion, this means we can tailor the thrust time grain, which leads to better performance, operational flexibility, and even tailorability over the spectral release of pyrotechnics. In the high explosives application, we can then lead to tunable charge initiation for better effects, enhanced safety, and also lead to innovations such as dialer yield, where you can change the output of your warhead as required. It's also great for very volume-constrained environment as well, and we can come up with warheads that result in less collateral damage. In gun systems, we can tailor the release of gases over the interior ballistics cycle, leading to better performance for gun barrels around their performance limitations. In hybrids, which I spoke to earlier, we can control the geometry and then the available surface area of the same, resulting in enhanced mixing between the fuel and air or fuel and oxidizer mixture. On top of the performance benefits as well, should we be able to demonstrate the utility of 3D printing of energetics across all the application spaces, it will allow agile and geographically agnostic energetic material and inert component production, facilitating both responsive and reactive space access and offering logistical and strategic advantage to the warfighter, including on-demand printing, potentially in theatre. DST has active collaborations with industry and academia, both in country and abroad, along with other defence organisations. Nanoenergetics are energetic materials that contain nanoparticles that have a particle size with a diameter of 100 nanometers or less, where material properties change significantly at this scale compared to traditional energetic materials. So to gain a bit of an appreciation of the scale, 100 nanometers is the same size as a virus, or 1,000 times smaller than the diameter of a human hair. So these properties give munitions based on nanoenergetics more energy output for a given volume and also reduced vulnerability. So for a given volume, we can create an enhanced effect on target, resulting in improved probabilities of kill, but we can also achieve smaller sized warheads for for the same energy output. And this is because by using nanoparticles, there's a much greater surface area which improves the chemical reactivity, particularly between the binder matrix and the solid fuel itself, which leads to better solubility and an enhanced streamlined process for manufacturing. Also, because we're using nanomaterials, the voids which may be present in these materials are also at a much smaller scale. So it results in munitions that have better or less sensitivity and less vulnerability to external threat. So they're great in environments that have very high temperatures, vibration, or even G-loading as well. So applications such as high-speed systems, penetrating warheads, or environments that require a smaller volume, such as swarming systems. It's a very emerging research area, and there are currently only a few players, and these are Russia, China, the US. Recently, Australia is also getting into this area, and we have an active collaboration with ARDEC, who are producing nanoscale polymer-coated energetic materials on the pilot scale. Finally, a novel processing technique is called resonant acoustic mixing, or RAM. RAM uses very low frequency but very high intensity acoustic energy to create Faraday waves or surface instabilities at the slurry air mixture of your mixing vessel. When this couples with the walls of the mixing vessel, it creates very intense recirculation zones which allow us the rapid and uniform mixing of highly viscous slurries, liquids and powders. An example of this mixing potential is shown on the video on screen, which is a very high solids loading mixture of a propellant, and just above from the mixture of two different colours of Play-Doh as well. This gives us the ability to mix very high energy loaded propellants by adding more solid components into the propellant, along with very hard to process materials such as nanoenergetics. This allows us to add energy above which has not been traditionally possible with conventional processing techniques. It's also very safe, as now we have a contactless method of mixing that doesn't use blades or impellers, and it also gives us the ability to mix in situ. So if we have a rocket motor case or a warhead as well, we can mix in that case that it's contained in. We remove some of the material transfer challenges as well from mixing in a container and pouring it into a case or into a warhead as well. Better performance, less porosity from that process is introduced, and also less waste as well. The final topic that I wanted to talk about is a new class of propulsion system. It's what was known as a pressure gain combustion or rotating detonation engine. It actually operates on a different thermodynamic cycle. You're no longer burning the propellant, you're actually detonating the propellant, which means there's more energy available for work. It operates at a higher pressure, which means we can gain more efficiencies from the propellant as well. So the way it operates, a RDE is an outside chamber with an internal concentric chamber as well, and the combustion chamber is a very thin, highly circumferential annulus inside. Just before the combustion chamber, a fuel and oxidizer mixture are either mixed just before and fed in through a ring of micro nozzles, or mixed inside the chamber itself, and it's detonated with a tangential detonator. So a detonation wave is established inside of the case, which continues very quickly around. Typical pressure gain combustion is done via mechanical switches, but in this system here, when the detonation wave passes, it's a massive increase in pressure, which blocks that ring of micro nozzles. So there's no backflow. Once that high pressure detonation wave is passed, it allows for the ingress of fresh fuel and oxidizer mixture, and so the system is self-regulating. It also means two surfaces are exposed, so it's twice the thermal management. It operates in two configurations. One is a air breathing configuration where it ingests air from the environment, and the other one is a rocket configuration as well. Sorry, I should have said when the fuel and air mixture is successfully detonated, it is highly rotational, and when this moves through the combustion chamber, it reaches a nozzle, which then turns the fuel from highly circumferential to axial, developing thrust. There are a lot of benefits for this type of propulsion system over traditional systems. Some of these benefits come from just using a higher ISP, so better thrust out of your system, but you can also generate greater range. The combustion chamber of an RDE is typically tens of centimetres long compared to, at the very high speed interface, a metre or 2 metres in the case of ramjets and scramjets. So with this highly compact system, you can now afford yourself more fuel or more warhead or more payload to orbit as well. So you result in better survivability, better lethality, better performance. There are still many challenges. Thermal management is obviously very difficult. It rotates at thousands of cycles a second, and that environment is very violent. Stability is still an issue. How does the inlet, ingesting air, interact with your rotational performance of the engine? Fuel operability, you have to select a fuel. In some cases, if you detonate a fuel, it actually won't be able to progress around that very narrow annulus, and you'll result in flame out. Finally, to experimentally test is tough because a rotating wave moves around thousands of times every second. It's also a very violent region. Sensors don't survive very long in that environment. To also ensure the numerical validity, you need to come up with combustion models, but these require tiny time steps, very refined meshes, and they have a range of underlying physics. Combustion, compressible flow, rotational, 3D, regions of low and high speed, so the computational overhead is massive. But the key opportunities here are for high-speed systems due to their compactness, as well as for responsive space access if you're using a liquid system. Also, decoys or targets, because this system has a relatively low takeover Mach number, so they could be used in this place. Finally, energy generation. They could replace traditional energy systems such as turbines. However, there is a fairly long development cycle until this can be fielded. So this is a pretty cool new technique. And with that, that is the end of the presentation. So just to summarise, each class of propulsion system has a range of pros and cons that I've talked about today. And this is highly dependent on the mission requirement, the application, the risk appetite, and the level of investment required to actually realise an operational capability. DST is conducting significant research into many of these propulsion classes, providing a real step change in performance to defence. If you want to talk any more about the research activities that I've talked about today or wish to engage further, please contact myself or one of the other authors on this presentation. Thanks, and open up for questions.